Good morning, everybody. Last time we started discussing about Markov decision processes because that's the starting point for then introducing reinforcement learning. So let me quickly recap what we have seen towards the end of the lecture, which is the definition of a Markov decision process. So a Markov decision process is a way basically to represent the dynamics of the system that you want to control. It's defined by this tuple that contains the state space, which is supposed to be a discrete space. So the state can only take a finite number of states. The action space, the probability transition matrix, which is the matrix that defines the probability of transitioning from a state to another state given a certain action, the cost, and the discount factor gamma. We have defined what a policy is. A policy is nothing more than a mapping from state to actions, which can be either deterministic or stochastic. If it's stochastic, then for every pair state action, you have a certain probability. If it's deterministic, then for every state, you have an associated action period. More often than not, we're going to assume that the policy is deterministic because for robots, typically that's what you want to use. Then a very important concept in Markov decision processes is the concept of the Q function, which is a function that maps a given state and a given control to a scalar. That scalar represents the total cost over an infinite horizon that you would pay if you start from the state X, you apply the control U, and then starting from the second time step, you follow policy pi. So it's actually a function of three things: the policy, the initial state, and the initial action. It's very similar to the concept of the value function. But the value function does not depend on the initial action because the initial action is supposed to be taken following the policy pi. Whereas here, the initial action U could be taken from a different policy, which is not pi. That's the only difference between the Q function and the value function. Similar to the value function, the Q function can be written in this recursive way where you define Q as a function of Q itself, which is going to come useful later for defining learning algorithms. So the Q function can be computed as the cost associated to the current state and control plus discount factor times the Q function associated to the next state and the action that would come applying policy pi at the next state. And this object here actually can be rewritten as simply the value function of the next state for the policy pi. Now we can also introduce the concept of the optimal value function, which is the value function associated to the optimal policy, so the one that minimizes the discounted summation of the cost. So the definition of the optimal value function is simply this one. Among all possible value functions, you choose the one, the policy that corresponds to the minimal value function. That gives you the optimal value function. And you can do the same for the Q function, which is also called action value function, if you want to use a more descriptive name. And sometimes, well, we are not going to use this much, but sometimes you may find this writing here, which may look confusing. But what this actually means to say that a policy is smaller than another policy, it actually means that the value of a policy is smaller than the value of another policy. It's just an overloading of the operator. The optimal policy can be computed from the optimal action value function by simply looking for the minimizer of the optimal action value function. So this is very important because this means that if we know Q star, so the optimal action value function, then it's almost trivial to compute the optimal policy, which is actually what we really want to find when we do policy optimization, which is what reinforcement learning does. So pi star is our true objective, what we want to compute. And this tells us that actually if we manage to get Q star, we're very close to getting pi star, because then we just need to find the minimizer of Q star and we have pi star. So this optimal action value function is going to be like a proxy objective that we want to find for then obtaining pi star. So many reinforcement learning algorithms actually don't directly try to find pi star, but they try to find Q star instead because of this. Because once you have Q star, it's very easy to get pi star, especially in the discrete setting, where this minimization is a minimization over a discrete space. So you just have to evaluate Q star for all possible values of the action space and then pick the minimum one. So it's a very easy minimization in that case. The same can actually be said about the value function, almost. Here I forgot a star. So if you know the optimal value function, you can do kind of the same thing that with the optimal action value function, but there is a disadvantage if you know V star instead of Q star. Can you spot it? Why is this minimization like easier than this one? Look at what we are minimizing here. Sum, yeah, but minimizing sums is not difficult. So in reinforcement learning, remember the typical assumption is that you don't know the MDP, the Markov decision process. You can just observe it, which in a robotics context would be you don't know the dynamics of the robot. You can just apply control inputs and see what motion comes out of it. So even if you know V star, can you actually do this minimization?
We can know the cost.
So the cost, it's true that in reinforcement learning, people try, I mean, not try, but like to say that they don't need to know the cost. But it's a quite silly assumption, in my opinion, because the cost, I mean, it's you who defines it. So I think it makes no sense to insist on this assumption that you don't know the cost. I mean, everybody knows the cost, but there is something else.
You don't know F of X.
Yeah, we don't know F, or at least that's the assumption. So it's better to know Q, because if you know Q, you can directly minimize it and obtain pi. Whereas if you know V, then you also need to know F and to know L in order to obtain pi.
F is not the probability matrix.
Yeah, it's equivalent to that.
And we don't know the probability.
In reinforcement learning, the assumption is that you don't know it. No. You can just basically observe the system evolves. In practice, however, I would say that in robotics at least, this assumption does not hold because most reinforcement learning algorithms are actually running in a simulation environment before being applied on the robot. So all the learning happens in simulation. And if you have a simulator, then you have F. So it's not really true in the context where they are applied in robotics. It's not true that you don't know F. The key difference I would say in robotics is that if you do trajectory optimization, you need to know F, and you also need to know how to compute Jacobian of F, because if you do gradient-based optimization, you need the derivatives of F as well. Whereas in reinforcement learning, you just need F. You don't need the derivatives of F. So in practice, I would say the main difference between RL and optimal control is that optimal control is derivative based and RL is derivative free. But they're both model based for the way they are used. In theory, of course, RL you could also apply it directly on the robots, but in practice, it's very hard to do that because of safety reasons. You don't want the robot to break. And because of also sample requirements. If you need to take 10 million samples on a real robot, it would take ages. But in simulation, you can do it because you can parallelize. And very last slide, Bellman's optimality equations. So here you can see a bunch of those, which are showing how V star and Q star are related to each other. Nothing particularly interesting or deep here, I think, to observe. It's just a relationship between V star and Q star. We're going to come back to some of these equations when we need them later. In general, I mean, what we can say is that these are nonlinear equations, contrary to the one we have seen before for the Markov chain, where to compute V, we had a linear system of equations to solve, if you remember, which was simply V equals C plus gamma PV. So in the case where the policy is fixed, or you have an autonomous system and you want to compute the value function, you have a linear system of equations, which we could solve just by inverting a matrix, basically. Here, since we have also to compute the policy, because it's a Markov decision process, everything becomes nonlinear. Can you see what is making it nonlinear? For instance, this one, which is very similar to the one I've written down before. Why is this a nonlinear equation in V star? Yeah, but no, because I mean, you should think of it as V star equal mean of L plus gamma P V star. It's the same thing, just written in a different form. So why is this nonlinear? And this one instead was linear. So this is linear, and this is nonlinear.
Just the minimizer function that is nonlinear.
Yeah, it's a minimizer operator, which makes it nonlinear.
But why is it nonlinear?
Well, the mean function is a nonlinear operator. So in this case, we have no closed form solution for solving these equations, and we're going to rely on iterative algorithms. And actually, the iterative algorithms that we need to use for solving these equations are the so-called dynamic programming algorithms, which is the next subject. So before we move on to the next subject, just I already wrote it on Classroom. We're gonna skip one lecture towards the end of November. So I think it's the 24th, if I'm not mistaken. And then, of course, the 8th of December is also no lecture because it's a national holiday. So yeah, we have to skip these two lectures, and we're still very well on track. We're gonna end the lectures way before the end of the semester, so it's no problem at all. But just beware, don't show up in class on those 2 days. Also, another piece of information. Well, we have published the marks for the first assignment. I guess you've seen that yesterday. And we have also published the second assignment. So you have 10 days for completing it. It's an assignment on optimal control. It's a different kind of application of optimal control where you have to do path tracking instead of trajectory tracking. So you have a geometric path that you want a robot manipulator to follow with the end effector. It has the shape of like an infinity symbol. And so you don't know the timing law, basically, that you have to use for following this path. You can go slow on certain parts of the path, and then you can go fast on other parts of the path. That's a free choice, basically, of the algorithm. So you need to formulate the problem a bit differently from what we have been doing before. Everything is explained in the text of the assignment, so you just read that. You can start, of course, from the codes that we have been using during the lab sessions in class to modify it so that you get this path tracking instead of trajectory tracking, which I think is a very useful thing to know how to do in practice, because that can happen. Like, for instance, if you want to have a robot that performs a cut with a laser, you care about the shape of the cut. You don't care about how fast it goes in every moment. So I think there are many practical use cases where you need to formulate the problem in this way. Okay, let me know if anything is not clear about the assignment. You can ask me questions by email. Always send the email also to Elisa. She's the one who is preparing the assignments and evaluating them. So it's important that she's in copy. Otherwise, I think that's all for me. And we can keep going, start talking about dynamic programming. So dynamic programming is not reinforcement learning yet. It's still considered like an optimal control methodology. Indeed, we have mentioned dynamic programming in the past when we discussed different optimal control families of methods. If you remember, dynamic programming was considered a global method, so trying to find the globally optimal solution of the problem for discrete settings. So settings in which the time is discrete. Here, since we are talking about dynamic programming applied to Markov decision processes, not only time, but also states and actions are going to be discrete. But there are also versions of dynamic programming that can be applied to continuous spaces for states and actions. So dynamic programming, as I said, is not reinforcement learning, it's still optimal control. So why do I teach you this? Well, it happens that a lot of reinforcement learning is based on dynamic programming. So I think it's very natural to go first through dynamic programming, because there we understand the key concepts, and then we just extend them to the case of reinforcement learning. And Main difference is going to be that in dynamic programming, we're going to assume full knowledge of the Markov decision process. So we know the dynamics of the system. And then to extend it to the reinforcement learning setting, we just have to relax this assumption. So assume we don't know the MDP. In dynamic programming, there are two classes of problems that can be solved: the prediction problems and the control problems. Actually, the main reason we go through the prediction problems is that that's instrumental then for solving the control problems. So the prediction problem is you're given a Markov decision process, a policy, which is fixed, and you want to compute the value function associated to that policy. This is a simpler problem. Instead, the control problem is the following one. You're given a Markov decision process, and you want to find at the same time the optimal value function and the optimal policy. This is much more difficult. So we're going to start with the prediction problem, and then we're going to move to the control problem. Before we delve into the algorithm, let me first quickly discuss this issue here. In optimal control, we have been used to working with a finite horizon. Instead, now in reinforcement learning, we're going to switch to the infinite horizon setting because that's where all reinforcement learning or most reinforcement learning algorithms have been developed. So in the finite horizon setting, the theory of dynamic programming looks a bit simpler, but that's the setting that is mostly used for then deriving optimal control algorithms. And a very important thing to notice is that when you have a finite horizon, the policy and the value, they both depend on time. And if you think a moment about it, that makes a lot of sense. So the optimal thing to do depends on how much time I have left in my horizon. So if I want to get as close as possible to that point over there, which I cannot reach standing here, if I have very little time, the best thing to do would be just to bend over and try to get close, even though I cannot reach it. It doesn't matter because I don't have enough time anyway. If I have a longer time horizon in front of me, the best thing to do is to stand up and walk there because I have enough time. Even if that means getting further away for a little while, because I need to walk to the right of the desk to reach that point. So the optimal thing to do in general depends on how much time you have in front of you. So it's reasonable that in the finite horizon setting, you have this dependency on time. In the infinite horizon setting, the horizon that you have in front of you is always the same. That's also something we discussed in model predictive control, if you remember. That's why we have all the recursive feasibility and stability issues in model predictive control, is because the trajectory that we optimize keeps changing, because the horizon that we look at is different every time because it's not infinite. So in the infinite horizon setting, instead, the horizon is always the same, and so time doesn't matter anymore. So the optimal policy, the optimal value function, they are both time independent. And that's why we're not going to factor in time when developing the algorithm. The theory is a bit more complex in the infinite horizon setting, but we'll see that the solutions that come out of it are very actually simple and elegant. And this is mostly used in reinforcement learning. Also, in case your problem is not really infinite horizon, but you have a quite long horizon, very often in practice, you can use the infinite horizon setting because that's a good approximation of what you would have with a finite horizon, since it's quite long. So this can be applied also to use cases where the actual horizon is finite, but it's sufficiently long that you don't want to care about time. And you can adjust the discount factor gamma so that the actual part of the horizon that matters actually matches your real horizon for the use case you're working with. Because depending on how you tune gamma, the discount factor, then what happens sufficiently long into the future doesn't matter anymore because it's multiplied by gamma to the power of the time step, which goes to 0 as the time step becomes large. So by tuning gamma, you can actually adjust how much into the future the policy looks into. Okay, so let's start talking about dynamic programming. All the algorithms we are going to work with rely on these two operators, which are called Bellman operators. These are operators that act on a value function. So they take a value function as input and they give you a value function as output. So they are modifying a value function. The first one is called the Bellman expectation backup operator. We're going to represent it with this symbol T pi. And it works in this way. It takes as input a value function V, and it gives as output a new value function, which is computed in this way. It's computed by evaluating the cost plus discount factor times probability transition matrix times the input value function. And if you remember, this expression is very similar to the one we have seen before. So when we define the value function in the Markov chain, we said that the value functions should satisfy this expression here. So it's, in jargon, we say that the value function is a fixed point of this equation. Because if you apply this, if you compute this for the value function, you get exactly the value function. If you do it for some other function, which is not the value function, you don't get the same output. So the value function is a fixed point, because if you see this as something that you apply iteratively over a function, it stops moving, stops changing when you reach the value function. So this Bellman expectation backup operator does exactly this. It modifies a given value function according to this expression. The only difference you can notice is that here we have all these superscripts pi, because here we're talking about a Markov decision process. So we have control inputs and we need to define how these control inputs are computed. So these superscripts pi, they're saying, well, the control inputs are going to be computed following policy pi. Whereas when we wrote this before, we were in the Markov chain context where we didn't have any control input, so we didn't need the superscript pi. But apart from that, it's exactly the same. And then we have the Bellman optimality backup operator, which we're going to represent simply with the symbol T, because it does not depend on a policy pi. And this is very similar to the expectation operator, but just we are adding a minimization in front of it. So we take a value function as input, and then we spit out a new value function, which is computed by solving this minimization for every state. So we are simply, it's basically the same one we had before, but instead of evaluating U with a fixed policy, for every state, we figure out what is the optimal U that minimizes this expression. And remember, here we are in a discrete space setting. So this minimization is actually evaluating this expression for all possible values of U and then picking the minimum one. So very straightforward brute force minimization over discrete space. It's nothing complicated, no gradients, no Newton's method. Here is brute force, evaluate, find minimum, period. Here I just wrote it in a different way, which may look a bit more familiar because I explicitly state the dependency on the state, which is implicit instead here, but it's exactly the same meaning, these two lines. And here I'm using the probability transition matrix, whereas here I'm using the dynamics notation, assuming that the system is deterministic, of course, otherwise I cannot use it. Okay, so these two operators here, T-pi and T, they're gonna be the core operators for the following algorithms for solving the prediction and the control problem. And let's start now with the prediction problem. Yeah.
The Bellman operator return the value function evaluated on a policy.
Yeah, it's for a fixed policy. That's why it has this superscript pi.
We have already used V with a policy before, and this V and after
V pi.
V pi is the same.
So here V can be actually anything. You can think of it as a vector, because the value function for a Markov decision process is basically a vector, where you have one value for each state. Since the states are finite in number, you have maybe, I don't know, 1,000 states, then V is a 1,000 dimensional vector, where each item of V is giving you the value of a given state. So here, when you think of applying this operator to a value, you can think of it as the value being a vector. And this is a function that takes a vector as input and gives you a vector as output. And this vector that is taken as input can be actually any vector. It's just a vector with 1,000 values in my example. Can be anything. Then, now that we are going to see the algorithms, we see how this can be used to compute something that is really a value function and not just a vector. Okay. So I think that now with this slide, everything should start to make a bit more sense. So bear with me for one more slide and then we discuss. So we need to solve the prediction problem, which is evaluating a given policy pi. And by evaluating, I mean computing the value function of that policy. So the algorithm is called Iterative Policy Evaluation, and it works in this very simple way by applying iteratively the Bellman expectation operator. So the first operator that we have introduced in the previous slide. So you start with an arbitrary estimate of the value function, which we call V0. In practice, this can be just a vector with all zeros. It doesn't need to be a good estimate. It can be any estimate. And then you iteratively apply the Bellman expectation operator. So you update your V0 in the following way. So for every state in your Markov decision process, you compute the cost for that state and applying the fixed policy pi. You sum to that discount factor times your current estimate of the value evaluated at the next state. Again, assuming you're using policy pi. And that gives you your new estimate of the value. And remember, this initial estimate of the value can be total nonsense. Doesn't matter. So typically it's going to be 0. And that gives you a new estimate of the value, which is going to be a bit better than the one you started with. And the idea is that every time you update the value with this operator, you're getting something that is a bit closer to the real value of that policy pi. And eventually this converges to the real value v pi. So in the limit for k going to infinity, you get v pi. Of course, in practice, when you do this, you don't go to infinity, you stop eventually. Because when you're sufficiently close to v pi, you're typically satisfied. I mean, it's always the same principle. We are looking for good approximations, not for exact solutions. Any idea how you would decide when it's good enough and you can stop? Because you don't know v pi, the real ground truth v pi, so you cannot compute the difference between what you have and the real solution. What do you think would be a good strategy?
The gradient of v pi is close to 0.
So v pi is the ground truth, so you don't know it. You know vk.
And then vk to v plus 1 or k minus 1 in this case, I guess.
Yeah, basically you look at the difference between vk and vk plus 1. And when this difference is very close to 0, you stop.
Can you repeat?
Yeah, you basically monitor. Let me write it down. When vk plus 1 minus vk in norm is below a given threshold, stop. So I don't know if you have any intuition at all for why this works, but I think I can give you some intuition. So suppose v0, which is your initial guess, is 0 for every x, which is a very reasonable initial guess for the value function if you don't know any better. Then if you apply this algorithm, v1 for a given state x is going to be the cost for that state applying the policy pi plus gamma v0 of the next state. But v0, we said that it's going to be 0, which is our initial guess. So this is simply the cost for every state. So after you have done one iteration of this algorithm, your estimate of the value function is simply the cost associated to that state applying policy pi. Then when you do a second iteration, what you get is the following. And v1, we said, is simply the cost associated to that state. So this is equal to L of x ix plus gamma L of x prime pi of x prime.
Prime being
the next state.
on the next stage.
Yeah, x prime, I mean the next state. Can do that for another step. V3 of x is going to be, well, the cost plus gamma times V2 but V2 is nothing more than the cost for that state plus gamma, the cost of the state after that one. Which I can rewrite again. I don't know if you see where this is going. Basically, at every iteration of the algorithm, this summation of discounted costs is growing. And we know that the real value is just this summation going to infinity. So of course, as the number of iterations of the algorithm goes to infinity, our estimate of the value converges to the real value. And the reason why we can stop at a certain point and be happy with that is because eventually the terms that we are summing are getting smaller and smaller because they're multiplied times gamma to the power of k. K is basically the number of iterations of the algorithm. So after 100 iterations, you're just adding your cost multiplied times gamma to the power of 100. So if gamma is 0.9 or even 99 to the power of 100, it's a very small number. Did you get that? So this is not exactly how the convergence of this algorithm is proven. This is just to give you some intuitions what's going on behind. Also because here I'm assuming that I'm starting from this guess of the value, which simplifies a bit the math. But this algorithm converges no matter what initial guess of the value you provide it with. The reason is that even if this was not 0 but was something else, basically it would appear here pre-multiplied times gamma to the power of the iteration number. So again, as the number of iterations goes to infinity, this multiplication coefficient in front of it goes to 0. So your initial guess V0 doesn't matter as the number of iteration goes to infinity. Okay. So this always converges. And with this, we have solved the first problem, the easy one, the prediction problem. So given a policy, find the value of that policy. Now we need to solve the more interesting problem, which is given a Markov decision process, find me the optimal policy. That's the so-called control problem. And here we're going to see two main algorithms for solving the control problem. One is policy iteration. The other one is value iteration. So let's start with policy iteration. So this is the pseudocode of the policy iteration algorithm. You start with an arbitrary guess for your initial policy, as usual. Can be arbitrarily bad. Typically, we're going to start with just 0. Then you iterate for theoretically an infinite number of iterations, but of course, we're going to stop early in practice. And at each iteration, you have a two-step evaluation, a two-step process. The first step is evaluate the policy. So compute the value function corresponding to your current policy. And we have just seen how to do that because that's the policy evaluation algorithm we have just described. So this step here corresponds to using the algorithm we have described in the previous slide to get the value. And then the second step is called the policy improvement step because it boils down to improving the policy. And the way you improve the policy is you find the action U that minimizes the current cost plus discount factor times the value of the next state, where the value is the value you have just computed in the previous step. So it's the value associated to your current policy. So again, remember we are in a discrete space setting. So the value function is a vector. The policy function is a vector because you have just one action for every possible state. You have, I don't know, 1,000 states. So the policy is a vector with 1,000 values. And for each item of this vector contains the action corresponding to that state. So if your action space has, I don't know, 10 possible actions and you have 1,000 possible states, then you can think of your policy as a vector with 1,000 elements, and each element contains a number between 0 and 9, which is the action. It's very different from what we have seen in optimal control and robotics, but we're going to get back to that setting eventually. But reinforcement learning comes from these modeling choices of discrete spaces. So when we do this minimization here, we have this V, which is a vector, and we're going to take the component of this vector corresponding to the state that is computed by my dynamics function. So the dynamics function is going to output an integer value, which is the index of the state which we reach. We take that value and we do this evaluation. We evaluate this expression here for all possible actions, and we take the minimum one. Or better said, we take the action that minimizes this expression because it's an argmin, not a min. So every time we try to find the action that is optimal with respect to the value function of the current policy. And that gives us a new policy. And we can guarantee that the new policy is never worse than the previous one. So at every step, we are improving the policy a little bit, or at least we are not making it worse. And this, as the number of iterations goes to infinity, converges to the optimal policy pi star. And of course, the optimal value function v star. Because once you have the optimal policy, if you evaluate it, you get the optimal value. So what happens is that basically the policy is always going to improve, except when we reach the optimal policy. At that point, it stays stationary. Because of course, you can no longer improve once you're at the optimal policy. So at that point, you're going to stay the same. So here in class, I'm not going to show you the convergence proof of these algorithms, but in the slides I've uploaded on Google Drive, you have an extended version of these slides, which contain also the convergence proof, I think, for all three algorithms. They're not too complex. So if you're a bit mathematically curious, I suggest you to take a look at them. They're not strictly required to pass the exam, but I think if you can understand the proofs, you understand better why the algorithms work. And a key insight that comes out of the proof is that for these algorithms to converge, you really need to have gamma that is smaller than 1. As in the previous case. Because if gamma is 1, then gamma to the power of 1000 is not a small number, it's just 1. And so you don't have this convergence. At least you don't have a convergence guarantees. It could still converge for different reasons, but you cannot guarantee that it always converges. Okay. I think it's a good moment to take a break because I know this is a quite dense lecture in terms of content, so you can digest it a little bit. I'll see you back here in 10 minutes at 38. Okay, so this is the first algorithm for doing control, so for finding the optimal policy for a given MDP. The main bottleneck of this algorithm is actually in the first step, in the policy evaluation step, because every time we hit this line, we have to evaluate a policy. So we have to find the value function of a given policy, and that we have seen how to do it. It's basically the iterative policy evaluation. In theory, that needs to go for infinitely many iterations to converge. So you can think of it as if every time you have to do this, you have an infinite for loop. Of course, in practice, you're never going to make it run for infinitely many iterations. We're going to stop early, but it may require many iterations to get a good estimate of this value. So a very reasonable question now would be, what if we do an early termination of the policy evaluation step? So instead of evaluating the policy to convergence, we just do a partial evaluation of the policy. So we run the policy evaluation algorithm, but for, I don't know, 10 iterations or 5 iterations. If we do that, what we obtain is the so-called modified policy iteration algorithm, which is just a little variation of policy iteration, which early terminates the evaluation process of the policy. And there is an interesting aspect here, is that if we stop this evaluation process only after only one iteration, which is of course the bare minimum we can do, then we get a new algorithm. which is called value iteration, which is the second algorithm I was talking about before. So you can see these two algorithms, policy iteration and value iterations, as actually two special cases of this more general algorithm, which is called modified policy iteration, which performs MK iterations of policy evaluation. So if MK is equal to infinity, then you recover policy iteration. If MK is equal to 1, you get value iteration. And if instead MK is something in between 1 and infinity, well, you get something in between these two extremes. And now we can analyze in more details what happens when MK is equal to 1. So when you do exactly one iteration of policy evaluation. So we can go back to policy iteration and think a bit about that. So what happens if here in this step, we only do one iteration of policy evaluation? And let's remember what policy evaluation is. Policy evaluation is this process here. So in the example that I did before, it means that basically we stop here. We stop after the first iteration of the algorithm. Of course, we're not always going to have the initial guess, which is equal to 0. Otherwise, we would make no progress at all. We're going to have an initial guess, which is something a bit meaningful. But we basically stop doing this. So we update the value just in this way, by looking at the cost of the current state, applying the given policy, plus discount times the current guess of the value evaluated at the next state. That's it. So when we do the policy evaluation step, we are just doing one iteration. And then we take this value, which is no longer the real value of the current policy, it's something else. And we update the policy according to that value. So by acting greedily, so minimizing according to that value. So it's something, I mean, it has a profound change in the algorithm. And if we try to write down the equations of what happens, it's basically what I've written down here in blue. So this would be one iteration of policy evaluation. So we start with a guess of the value, vk minus 1, and we compute a new value, vk, simply by following the policy evaluation algorithm. So we apply the Bellman expectation backup operator. This is not written in the slides, this part in blue. So maybe you want to write it down. And this is the new value that you have. And the policy that actually you're using for doing this step is the policy that you optimized, that you improved at the previous iteration, which is this one. And if we just write it with a shift of index to k to match the index we are using here, then pi k is the argmin of the cost plus gamma times the previous guess of the value, vk minus 1.
Is it vk or vn?
It's like always k. There is no n. So I just wrote here the policy improvements equation for iteration k minus 1. And here I wrote what we have for the policy evaluation step if we just do one iteration of the algorithm. And now that we have written them down, we can observe that actually what we are minimizing here is exactly the same thing we are evaluating here. They are the same. I have the cost, I have the discount factor, and I have vk minus 1. That's exactly the same value I'm using. And since they are the same, I can actually do both things just in one line, which is the following one. So since here, to evaluate the new value, I'm evaluating this expression using as action the action that was computed by minimizing the same expression. That's the same thing as saying that the new value is simply the minimum of this expression over u. Because what I did with these two lines is find the minimizer of an expression and then evaluate that expression for the minimizer. But that's the same thing as finding the minimum of the expression. I see you're confused. Let me write it with a completely different notation just to understand the concept. If I'm saying y star equal r min over y of gy, and then I do hy equal g of y star. These two steps are equivalent. To the following one-step process, which is hy equal min over y of gy. Can we agree on that? Okay. Finding the minimizer and then evaluating the function I was minimizing at the minimizer is the same as finding the minimum of that function. So this is exactly the same thing that's going on above. It's just that the equations are a bit longer and more convoluted, but it's exactly the same. So with the policy improvement step, I'm finding the minimizer of an expression. And then with the policy evaluation step, I'm evaluating the same expression at the minimizer. So I can do these two operations in just one line, which is finding the minimum of that expression. So since I can do both things with just this, do I even need a policy now to store a policy?
No.
No, of course, because there is no policy with this new way of writing it. The policy was just this intermediate thing, which in the new example would be y star, which I'm computing, but just then I can evaluate G at Y star, but in the new way I'm writing things, Y star does not need to be stored. I'm simply finding the minimum of this expression and that's it. And this expression in this case would be basically the value. So the new algorithm that I can obtain does not need to store the policy. It just needs to store the value. And that's why it's called value iteration. And the previous one was called instead policy iteration. I simply have my value, and at each step, I update it in this way by minimizing this expression, which depends on the current guess of the value, and it gives me the new guess of the value. Now we're going to see how it writes down nicely, but I think it's nice to derive it from policy iteration by setting the number of iterations of evaluation to 1. So this is value iteration. You start with an arbitrary guess for the value function, typically again 0. And then you need to iterate for infinitely many iterations. At each iteration of the algorithm, you loop over your state space. And you update your value, your guess of the optimal value, by performing this minimization. So you cycle over all possible state and all possible actions. You evaluate this expression, and for every state you find the minimum over all the actions, and that gives you the new value for your value guess. These 2 lines, we can write them in a very compact form by using the Bellman optimality operator, which we have introduced at the beginning of the lecture. Because that is basically what the Bellman optimality operator does. It updates the value, performing a minimization over the actions. And no surprise, the algorithm converges to the optimal value function. Otherwise, we wouldn't be discussing it. And then once you have the optimal value function, which you maybe don't care too much about, you can obtain the optimal policy, which is, of course, what you really care about, by simply performing one extra minimization, which is this one. So throughout the algorithm, you don't need to store the policy, but at the end, once the algorithm has converged, you need the policy. But if you have V star, it's very easy to compute pi star. You just find the minimizer of cost plus discount times V star of the next state, and that gives you the optimal policy. Which we said in reinforcement learning, this is not good because you need to rely on the assumption that you don't know the system dynamics, but here we are not still in reinforcement learning land. We are still in optimal control land, so we know the dynamics, and so doing this evaluation is not a problem. So I didn't write it, but this will be V star of the next state. So if I write the dependencies, we have a dependency on the dynamics, so we need to know it. But this is dynamic programming, so it's kind of optimal control, and the dynamic is known. I mean, we need to know the dynamics even inside the algorithms, because here we are using it everywhere. We are using it here when we do value iteration, and we were using it before when we were doing policy iteration, and we were using it even before when we were doing policy evaluation. So all these algorithms are based on the assumption that you know the dynamics. Because again, they are optimal control algorithms in flavor. And that's it. Those are the 3 dynamic programming algorithms I had to teach you today. So policy evaluation, policy iteration, and value iteration. And we're going to see later in the next lectures how especially policy iteration and value iteration are actually the foundation of many reinforcement learning algorithms. So if you manage to understand policy iteration and value iteration, I think you're in a very good place for understanding most reinforcement learning algorithms, because the core ideas are actually these ones. And I think it's easier to understand them in this context of dynamic programming, where everything is known, you know the dynamics, you know everything, rather than in the more complex context of reinforcement learning, where you also need to worry about the fact you don't know the dynamics. And so there are some extra steps we need to go through. But the really powerful key concepts of reinforcement learning, at least that's my belief, are already here. So having a good understanding of value iteration and policy iteration, I think, is the most important thing for understanding most reinforcement learning. Especially, I think it's super important to understand the policy improvement step, this one here. Because if you understand the policy improvement step, you're going to find it's coming many times in many algorithms of RL. I mean, most RL algorithms are based on this policy improvement step. And I think to really understand it, you need to go through the proof of convergence of this algorithm here. So policy iteration. So you can find it in the slides, and if you want to gain like a deep understanding of it, I suggest you go through it. It's not very difficult. I think the key insight is that once you have the value of a policy pi k, and you compute a new policy pi k plus 1 by minimizing this, the new policy cannot be worse than the previous one. And most of the times it's going to be better. And the reason why is that you're basically computing the new policy by saying, okay, if I'm in a state X, what I want to do is to find the control input U that minimizes the current cost plus the cost I would pay from the second step onward following policy pi k. Okay, so you're saying what I pay now plus what I would pay afterwards following the policy I already have computed. And if you reason in that way, the control input that you choose cannot be worse than the one that pi k would choose. Because you can always choose U to be the same one that pi k would choose. But maybe there is something better to be chosen. And so you can get something that is better than what pi k would choose. And so every time you go through this minimization here, the new policy that you obtain is a bit better than the previous one, unless, of course, you already had the optimal policy, which cannot be improved. Which, by the way, also gives you the termination condition for this algorithm. How do you decide when to terminate this? Because we said that for the policy evaluation, we look at how much the value has changed in the next iteration. And if this is below a threshold, then we stop. We didn't say when we're going to stop here.
I guess we just look at the policy at time step k+1 and time step k, and then also see the difference in between is like close to 0.
Yeah.
So calculate some kind of norm and then decide
Yeah.
the threshold.
That's the idea, but there is a bit of a difference, is that here, so why with policy evaluation, you really need to go to infinity to have convergence. Here, you don't. You converge in a finite number of steps.
Why?
It just happens.
But because it says that it turns to the optimal one at k going to infinity, that's not nice.
Yeah, I mean, here I wrote it for the in the limit, but what happens is that you converge in a finite number of steps in practice, which is a fake finite convergence because every step of this loop contains an infinite loop. So you're not really converging in a finite number of steps. But assuming that you have a way of here getting the true value somehow in finite time, then you need to go through this two-step process only a finite number of times.
So that would mean that we have to choose a threshold, but it's actually 0.
Yeah, you can get it to 0. Again, it's a fake finite convergence because it contains a process which requires an infinite number of steps. But just to say that here you can converge in a finite number of iterations for this loop. Okay. We still have a bit of time, so I suggest we move on and we talk a bit about the next subject. We're probably not going to be able to finish it in 20 minutes, but at least we're going to introduce it. By the way, next lecture on Monday, we can do a lab session. So we can start implementing the dynamic programming algorithm we have seen today. So value iteration, policy evaluation, so that you kind of start gaining an insight in how they work. So bring your own laptop. So model-free prediction. Here we start taking a first step towards reinforcement learning, because we start relaxing the assumptions that we know the Markov decision process, so we know the dynamics. But we do it only focusing on the prediction problem first. We're going to talk about the control problem later. So we are given a Markov decision process, which is unknown. So we don't know the probability transition matrix. We don't know the dynamics function f. We have a fixed policy, pi, and we want to estimate the value of the policy. So that's exactly the problem we have solved 1 hour ago, but now assuming we don't know the Markov decision process. So we need to observe how the system behaves and learn from the observation. And here we're going to see there are two main methods. One is Monte Carlo, and the other one is called temporal difference learning. Let's start with Monte Carlo, which is simpler, and then we move on to temporal difference learning. Actually, the idea of Monte Carlo is extremely simple. The value of a given policy is simply the mean return that you observe starting from a state and applying that policy. So if you observe what the system does when starting from a state and applying that policy for many times, you can just compute the average of the return that you obtain. So the return would be the summation of the cost from that state until the end. You do it several times and you compute the average, and that gives you an estimate of the value for that state and for that policy, assuming that everything is stochastic. If it's deterministic, you just need to observe it once because you're going to get exactly the same every time. But in general, remember, reinforcement learning thinks of the system as a stochastic system, and that's why you need to observe it several times. The caveat here is that this idea can be only applied if you have an episodic MDP, which means that your episodes must terminate. So there must be an end to the episode, so you cannot work in the infinite horizon setting, which is instead more common in reinforcement learning. This is going to be fixed by temporal difference learning, which is the other method we're going to discuss later. So this is the key idea. Let's see how it is detailed. So the goal is to learn the value of a policy, VPI, from episodes of experience collected under the policy pi. So what you see in practice is that you start from a given state, which you can measure, x1. You apply some control input computed by the policy pi. That gives you the control input u1. And you observe the cost L1. And you move to the next state, x2, and you keep applying the policy, observing states and observing cost until the end of your data collection. So this data collection follows the policy pi. This is what this symbol means. Then for this data that we have collected, we can compute the cost to go, which is nothing more than the summation of the cost observed at each time step, pre-multiplied by the appropriate discount factor. So the cost at the next time is discounted by gamma. In 2 time steps, it's discounted by gamma to the power of 2, and so on and so forth until the end. And remember, there must be an end, which in this case is capital T. And the value function is nothing more than the expectation of this cost to go, which, assuming that the policy and or the Markov decision process might be stochastic, may be different every time we go through a state. So we are not always going to see the same cost to go, even starting from the same state and applying the same policy, because we have stochasticity in the dynamics and possibly even in the policy.
Why do we use the discount factor if we have a finite?
Well, in this case, you're not forced to do it, but since we are in the reinforcement learning setting now, I'm going to keep using it. Of course, you just set it to 1, and it's like not having it if you don't want it. So the value is going to be simply the expectation of this cost to go. And so we just need to compute the average of this quantity as we collect data. So one way in which we can do it is the so-called first visit Monte Carlo policy evaluation. So the first time that you visit a state inside an episode, you increment the counter associated to that state. So you have a vector of counters, one for every state. You find the element of that vector corresponding to the state you just visited, and you increment it by 1. Similarly, you have a vector of cost associated to each state. You find the element corresponding to the state you just visited, and you increment it with the cost to go associated to that state. And then you can update your estimate of the value of that state, which is again a vector with one element for every state. You find the element corresponding to the state you just visited, and you update that by simply computing the ratio between the total summation of the cost to goes divided by the number of times you have encountered that state. It's an average. Total value divided by number of samples, basically, of that quantity. By the law of large numbers, as the number of times you visit that state goes to infinity, your estimate of the value is going to converge to the real value. You're just estimating an expectation using an average. There are two ways in which you can do that. One is called first visit Monte Carlo policy evaluation. There is another version which is called instead every visit Monte Carlo policy evaluation, because you can decide if in case you visit the same state more than once in one episode, you can decide whether you want to count that as 2 visits or not. They both work. So you can do whichever you want. We're going to implement the easiest one, which is the every visit version. It helps for the following discussion to also see how you can do this Monte Carlo value estimation in an incremental way. So instead of doing it in this way, where you keep track of the total summation of the cost to goes, and every time you recompute your estimate of the value, let's say from scratch, we can do this computation in a recursive way. So you can write the equation so that your new estimate of the value is computed as a function of your previous estimate of the value. And you just need to go through these simple mathematical steps. So the estimate of the value after you have collected n samples can be computed as the summation of the cost to go for every time you have visited that state divided by capital N. This is the way it is computed in the previous slide. So total summation of the cost to goes divided by number of visits of that state. I can write this in the following way by splitting the summation into 2 parts. I can just remove from the summation the very last term, so J capital N, and leave inside the summation the other n minus 1 terms. And then actually I can write this as n minus 1 times the previous estimate of the value, because the previous estimate of the value was simply this summation divided by n minus 1. Well, let me write that. B n minus 1 is the summation for j going from 1 to n minus 1 of jj divided n minus 1, which means that the summation for j going from 1 to n minus 1 of jj can be written as n minus 1 times Vn minus 1. So this is what I have exploited to write this. Okay. And basically, once I am here, I am done. I'm simply then rearranging the terms a little bit so that I have this way of writing it as Vn equal Vn minus 1 plus something, which is more convenient for what I want to show you later. But going from this to this is trivial. So you can see that as n grows, the update tend to 0, because as n goes to infinity, this 1 over n in front of the update goes to 0. So it's obvious that as I keep iterating, my estimate of the value are going to change by smaller and smaller amounts. So this is an interesting form for Monte Carlo to observe, because it's going to be very similar to the update law for the next method we're going to discuss, which is temporal difference learning. And so it allows us to compare Monte Carlo and temporal difference in a more direct way. Also, in case the system we are working with is non-stationary, so it changes with time, which is making it much more difficult to work with. Maybe we don't want the updates to our value to tend to 0. And so we can substitute this 1 over n that we have in front of the update with a constant factor alpha. In this way, we keep updating our estimate of the value always with the same amount of information, let's say. And this is a way to basically give higher importance to the samples that have been collected recently with respect to samples that have been collected in the past. It's not anything that we're doing in a very precise way, but just intuitively speaking, as we keep going, we should have the coefficient here, which becomes smaller and smaller, in order to give all the information the same amount of importance. If instead we use here a factor which is constant, that corresponds to giving the more recent information higher relevance than we give to the old information, so to the old samples. And if you have an MDP which is time varying, that makes a lot of sense, because the more recent information are more relevant than the old information. So you can think of this as a variation of Monte Carlo, which takes into account also the time at which informations have been collected and not only doesn't treat them all the same way. Okay, I think that's it for Monte Carlo. And since we have only a few minutes left, I wouldn't start the next topic. I think we better start it next time, which is going to be actually next Friday, because on Monday we do the lab session on dynamic programming. So I'll see you on Monday.